In this podcast, we're going to talk about how ATP can be hydrolyzed to form ADP, and then how we can phosphorylate ADP to store energy in the form of ATP, which is a lot of acronyms, but we'll get through it together. All right, so as we've been talking about, ATP is your energy currency for a cell. It's how we get work done in the cell. So let's talk about how this works. ATP hydrolysis, remember that word is using water to break ATP into ADP in inorganic phosphate. Here we can see a structure of ATP, of 1, 2, 3 phosphates. So this is how we store energy. When we cleave this phosphate bond to form ADP, which is right below, we're going to release 7.3 kilocalories of energy per mole. We can use this to drive processes in the body that may not be energetically favorable on their own. So essentially what it's saying is you can use this hydrolysis coupled with another reaction that may not happen on its own. If you do the two reactions together, you are going to make it more energetically favorable, and whatever reaction that you couple it with will happen, which is good because there's a lot of reactions in your body that aren't energetically favorable, but you need them to live. So the body's solution to that, hydrolyze ATP. That will release enough energy for the other reaction to occur. So ATP to ADP is a release of energy. However, your body goes through ATP molecules every single day, like Cadbury eggs at Easter. I will tell you what, ATP, it's estimated, exists only for about a minute in the body before it's hydrolyzed and energy is released. So if we made an ATP molecule and it instantly was hydrolyzed a minute later, we would be going through a lot of ATP. Thankfully, we have a way to make ATP from ADP. So we can phosphorylate adenosine diphosphate to form ATP. So we can actually do the reverse reaction. We can add a phosphate group on here and reform ATP, therefore recycling the ADP that is our spent energy source. So energy can be absorbed or stored. All right, so just to give you an idea, when we hydrolyze ATP into ADP, that's lower energy, we release energy. That negative sign is telling us that energy is released. When we add a phosphate or we phosphorylate ADP to ATP, energy is absorbed. So we're storing energy in that bond that we can then use to do work later on to couple with another reaction. All right, so let's look at this cycle in a more visual way. ATP, it's this phosphate that we're interested in. We can hydrolyze it. So say we have a reaction that's not going to happen on its own. We couple it with ATP, and all that energy released by hydrolyzing this phosphate bond is going to drive that other reaction. But what we're going to be left with is this low energy form of ADP. Thankfully, though, we can phosphorylate, so we can add a phosphate group onto ADP to reform ATP and go through this cycle again, so it gets recycled. Think of ATP like a charged battery. It has the capacity to do work. It's ready to go. If you were to put that charged battery into a flashlight and hand it over to your kids and they leave it on all night long, it doesn't have energy anymore. Okay, so think of ADP as being your uncharged battery that needs to go back on the charger. Okay, so we can recharge that by phosphorylating ADP into ATP so that we can use it again.